Good afternoon. Welcome back after lunch. My name is Stefano Zanero. I come from Italy. I am a PhD student and candidate at the Politecnico di Milano University, which is Italy's largest school of engineering. And I also am the CTO and founder of Secure Network SRL. Secure Network is a small startup business providing high-level consulting and technology transfer to the enterprise. Today, what I will talk about is how unsupervised learning IDSs, which are the topic of my research at the Politecnico, can or could be used to detect zero-day attacks. What I will do is to walk through a brief introduction which tries to build up the case for intrusion detection systems. I'm not here to try to sell you my idea, but I'd like to highlight a few points of why we would need an intrusion detection system, and in particular, an intrusion detection system based on learning techniques. Because if we do not understand clearly what it is that we want to achieve, it's difficult to try to evaluate our results. Then we will briefly look at the state of the art of intrusion detection. I will share with you my view of the state of the art, which you are not requested to agree with. In the whole presentation, I'd welcome and I'd value very much your input and your opinion, both during the presentation and afterwards. Because this is the presentation of research which is work in progress, and any input, any idea that you may like to share with me will be helpful to me in continuing my research. And then I will introduce you the types of algorithms we are using to build this type of detectors and some of the results. I will try to discuss with you if this is an hope or it's just an hype, and draw my conclusions. I will begin with a parallel, which is discomforting in my point of view, and I'd like to just begin by saying that I'm not trying to discuss political matters. You have more than enough political matters running on CNN right now, so I will stay clear of that. But I will invite you to think of what has happened in our world since 9/11/2001. And I recall what has happened to me a couple of days ago when I landed at Atlanta. And I've seen for the first time that the immigration is actually taking the fingerprint image and photographs of any alien entering the United States who is holding a visa. I do not hold a visa. I do not need one to enter the United States. And so they didn't photograph me. So they are actually photographing and taking fingerprints of visa holders and not of people who has not been cleared before, which seems not much of an improvement to me. But if you think of every type of defensive fortification we have built since the effects of 9/11, then you will see that we have mostly done what we can to raise costs, create distractions, and create annoyance. And if we reflect, if we are more secure today than we were 3 years ago, well, unluckily, it does not seem so to me. Certainly, what happens is that we feel more secure because we see a longer line at the immigration. We actually feel that controls are more strict and harder to bypass. But it's not a sure thing. And the basic reason for this, and the basic reason for the existence of my talk and my area of work, actually, is that the defender in strategy is always the part who is at a disadvantage, because the defender needs to plan for everything, while the attacker needs just to find one weak spot. And there is an interesting historical battle. I don't know if you have a passion for battles such as I have, but King Darius, king of Persia, I do not have the English translation for the right term, let's say king of Persia, versus Alexander Magnus. This was this great battle at Gaugamela Plains. So you must follow me through this little history lesson. 3 years before, Alexander Magnus and Darius fought at Issos. Issos is a place where there is a very, very narrow valley. And Darius, who was the king of the great state of Persia, had an impressive army, a really impressive army. Someone talks about 250,000 people, which for the time were huge. Alexander had perhaps 50,000, so he was outnumbered at a rate of 1 to 5. But at Issos, there was a narrow valley which could be defended very well with a small army. So Darius thought about this, and when he had to confront another time Alexander, he chose the battlefield, Gaugamela Plains, a very, very wide plain with not a single rock, not a single tree, just a huge and vast place without a single place to defend. Just maneuvers of a large army. And in this type of place, a rate of 5 to 1 means defeat, by all means. But Alexander had an advantage. He was a great commander. Alexander thought about Darius. And he thought that everything could change, but not the fact that Darius was a timid and a timid person, easy to scare. And so the whole army of Alexander, with Alexander on the head of the army, attacked the army of Darius, not in the flanks, which was the only reasonable thing to do for a smaller army, but straight in the middle, aiming to the place where Darius stood. And Darius understood what that meant. Alexander was ready to die and to bring all his men, all his troops, to death with him, but he had one single objective, to kill him before he died. And Darius fled. And when the commander of an army flees, the army disappears. Gaugamela Plains was the last battle of Darius. He was later killed by his own troops. So why are we failing today? We are failing because we are like Darius. We are building huge things. We are building impressive fortifications. But we are failing to think sensibly about what we are doing. And I won't go ahead in this line of reasoning, but I'd like to suggest you to read Beyond Fear by Bruce Schneier, which I found to be a great book. So, we cannot really defend against everything, but we must behave sensibly. We display defenses in the most vulnerable areas. We try to make deterrence a key point of our information security strategy. And that's what the immigration service at Atlanta is for. Not really for detecting people, but for displaying force. We can try to protect the systems as far as we can. That's sensible, that's reasonable. But at the end of the day, what we must keep in mind is that every system, every defensive system, at some time will fail. So we must plan the systems, not just for normal operations, but for failure. We must design systems that can withstand attack, the concept of multi-layer security, but we must also design systems that are tamper-evident, that make very difficult not to notice that an intrusion happened. What's so scary about intrusions is the fact that if the attacker is killed, you won't notice him until it's too late. And also, we must design systems that are capable of a speedy recovery. So, intrusion detection systems is all about Murphy's law. Because the only difference between a system that can fail and a system that cannot possibly fail is that when a system that cannot possibly fail fails, it fails in a totally devastating manner. And it's usually very difficult or impossible to repair. So we must plan for the worst, which is the mantra of intrusion detection. So we have said, we must design a system which displays clearly that it's been tampered with. Just think of smart cards. What's the key value in a smart card? That if someone tampers with it, he either destroys it, or anyway, it will render it so totally useless that we cannot help but understand that something wrong has happened. An IDS is basically any system which is capable of detecting intrusion attempts on an information system. So what I would like to share with you is this vision that an intrusion detection system, I'm an engineer, when I talk about systems, I don't talk about softwares. Because a software is a component of an intrusion detection system. And it's not the key component even. And an IDS is a system that works on an information system, on the whole of the information system, and not just on a network. So the so-called IDS software packages are a component of an intrusion detection system, but the key component of an intrusion detection system is the human, which closes the loop of the intrusion detection system itself. So again, a skilled human, one of the people in this room, looking at the logs of a system, is an intrusion detection system. He is capable of detecting intrusions. A skilled network administrator looking at a TCP dump screen is an intrusion detection system. If something wrong happens, there are good possibilities that it will catch it. A company who is maintaining your firewall and monitoring it is an intrusion detection system. Instead, if you buy a box, you plug it into your network, and you forget about it, that's not an intrusion detection system. It's an intrusion logging system, perhaps, but not an intrusion detection system. So an IDS is not a panacea. It's a component of a network security strategy. And it does not substitute a firewall. It was not designed to, no matter what Gartner thinks. Don't get me started. I worked for IDG, so I may be a bit biased. But, and it's kind of the cherry on the top of your network security system. When you have done your homework, you have built everything else, then it's time to think about a system for detecting intrusions. Otherwise, you don't need to detect them. You are pretty much sure that there has been an intrusion. You just don't know why. So it's basically the last component that must be added to a security architecture, not the first one. Also, detecting without reacting is useless. It's like having those awful burglar alarms on houses which begin to sound usually in summer when people are on holidays, and they keep on sounding and sounding for weeks before someone shuts them off. And no one cares about them sounding. So they are totally useless. most IDSs are exactly like that. And also, at the state of the art, reacting without a human supervision is something of a dream. Don't get me starting about IPS, please. Network defend thyself is a good slogan. Any Cisco guys here around? No? Good. But it's just a slogan. So in IDS, we find that a lot of different types of software that can be involved, beginning with your basic vanilla logging and auditing systems. You've got them, you don't use them. They are the most basic intrusion detection system component that you can find. There are also correlation systems. State-of-the-art correlation systems are some of the most awful pieces of crap I've ever seen, but they are there, and they are surely useful. There are also the so-called IDS software. And then there are also honeypots and honey tokens, which are not intrusion detection system by design, but can surely help in detecting intrusions, if used in some way. Basically, if you have a research honeypot, that's not designed for helping you in detecting intrusion. It's designed to making intrusions happen, actually. But if you design an honeypot or an honey token architecture for protecting your enterprise network, hey, that's a component of your intrusion detection system. You are also a component of that intrusion detection systems, by the way. The logic, basically, is always the same in all these systems. We are trying to catch those who are accessing illegally our systems by the means of what they are doing, because we suppose that they are acting differently than normal users do. If they are acting exactly as the normal users would do, we will never catch them. So we have two main ways to do this, the right way and the wrong way. No, it doesn't work in that kind of way, but we have the anomaly detection method and the misuse detection method. I think most of you are proficient with them. In the anomaly detection method, we basically try to describe what's normal and try to flag deviations. This is the basic concept of an IDS. The first IDSs, historically, were anomaly detection based. There are a lot of ways to build an anomaly detection system. The cool thing about anomaly detection models is that theoretically, since you are describing what's normal and not what's anomalous, when a new attack pops out, you don't care about it, because your system is describing what's normally happening on your network. So the new attack or the old attack is all the same for it. It's a deviation. And theoretically, this means that anomaly detection systems are able to recognize any attack, also a zero-day attack. However, there's a problem. They are awfully complex to build, and we will see they have also a plethora of problems that must be solved. But the key problem, the very, very key problem, is that they generate alerts that goes like, hey, something's wrong. What? Your guess. So misuse detection systems are actually more popular. I don't know, maybe someone has heard about Snort, someone has heard about Real Secure. These are all misuse detection-based systems. Yes, they have some small parts or some small components that do some anomaly-based detections, but that's not the key point. The key point of the systems is that they have a knowledge base of attacks, and they use only this knowledge base to recognize them. If it matches a signature, it's an attack. Doesn't match, it's not an attack. So when a new type of attack a new attack is created, when a zero-day is created, no one knows about it. If Otherwise, it wouldn't be a 0-day. And since no one knows about it, most probably, there is no signature to catch it. Also, if a new type of classes of attack is introduced, not always, but many times, it happens that the language that expresses the rules is not enough. It's not expressive enough to catch this new type of attack. There are problems for polymorphism. There are problems for other type of attacks. You may just want to walk out, arrive at Arbor Network stand, and talk with Tom Tacek about this. But there is one key point which makes misuse detection so interesting. It generates a cool alert which contains all the information about the attack. It says, hey, it's an attack against IIS web server, this version. This is the knowledge base article which states what to do to protect yourself. Uninstall IIS. And this is the patch for that vulnerability. So these type of alerts are something a network administrator can really act upon. Not there's something wrong. Go figure. But misuse detection alone is an awful idea. Anyone who has installed Snort and then thrown it away knows why. Because these systems need a continuous update. Many attacks are not known. Many 0 days stay in circulation for months, despite what Microsoft seems to think. It's not that like that every script kiddie in the world is just waiting their patches to reverse engineer the patch and create the exploit. The exploit usually has birth before the patch is released. And the misuse-based IDS will not, in general, recognize an attack for which the vulnerability has not yet been released. But even if the attack is known, attacks are polymorphs. And you might object, well, what's the problem? Also, computer viruses are polymorph, and we have built antivirus software which can detect polymorph computer viruses. Yes, but a computer virus is as polymorph as a computer program can be. And an attack, in the end of this skilled attacker, is as polymorph as a human can be. And that's very different. Just think about admutate. Think about all the possible ways to encode a string. Think about all the ways to evade intrusion detection systems that have been developed in past and continue to be developed. You have admutate, which basically encrypts or obfuscates the shellcode of an attack. And you add the signature to detect the code of admutate. But how many other types of code can realize the same function as admutate does? A misuse-based IDS does not only have problems in recognizing a new attack, it has also problems in recognizing all the attacks that are exploited in a new way. Unless there is some key characteristics which is in the attack and which is not anywhere else. So, since we have said that intrusion detection is a key component of tamper evidence, which is needed right when other systems, other components of our network security strategies are failing. So we need intrusion detection when there is an attack which has no patches for it. We need intrusion detection when there is an attack which we cannot really defend against. We do not need it for the PHF bug, which is old, awfully old, and still in the signature base of any IDS system. We do not really need it for catching the Nimda worm signature. Who cares if Nimda is still attacking my network? We need it to catch new things that are coming through our firewalls and which we do not know a single thing about. So detecting known attacks is something useful, I do not say it's not useful. I work with intrusion detection systems. It would be bad for me, for my career, to tell so. But detecting known attacks is half of the solution. And it's not even the half we are more interested in. But anomaly detection is awful all the same. Because we are tasked to describe the normal behavior of a system. If you want to think about it for a minute, how do you describe the behavior of a computer system? Which variables do you measure? Which characteristics do you take into account? How do you express their behavior? Statistically, mean and variance? Maybe for some variables this makes sense. For some other variables, this does not make any sense. They are completely random at first look. And which of the infinite models you have around you choose to fit them? And when you have chosen a model, how do you fix the thresholds that make an alarm fire off? In this case, what you are trying to do, fundamentally, is trying to describe the overall behavior of a system, of a networked system, with maybe hundreds of very, very complex computer systems. We were discussing this the other day. I don't remember with whom, but just think about, for example, the behavior of an application in an old-style Unix system. It does a little thing, and it does that thing always in the same way. You can describe it. You can model its behavior. You can model, for example, the sequence of system calls it uses. Now think of Internet Explorer, or Mozilla, by the way. It's all the same. No, it's not all the same, but actually, for my point, it's all the same. If you pick up a thing like Mozilla, or a thing like an electronic spreadsheet, they can do an awful and amazing array of things. How do you describe the normal behavior of such an application? Which variables do you measure? Which are the fingerprints of normal and abnormal behavior in this case? It's simply awfully difficult. And this base model, this discussion, is not just a philosophic point. It's the core of the problem. Because if you choose to measure 3 variables, and the attack you are under just shows up in a 4th variable, you don't see it. And if that attack, for example, shows up in the derivative of a variable, and you are just measuring it from time window to time window in a way that averages out that spike, you won't detect it. So choosing the right model to fit this type of things is not trivial. It's the core of the problem. And in any case, when you have done everything correctly, you still are left with that single problem which I stressed before. The alert says that something is wrong. And with most of the algorithms I will be talking about, you don't have really a way, unless some special things are provided, to reconstruct why the algorithm has raised the alarm. Think of, for example, for using a simple example, think of a neural network if you are proficient with that type of things. You have the inputs, you have an output, but it's awfully difficult if you are given an output to understand which of the inputs has caused the network to actually shoot out that output. And by the way, this also means that this type of systems are not, and probably will never be, suitable for IPS applications, unless you are ready to throw away an awful lot of babies with the dirty water. Our approach has been to study the application of unsupervised learning algorithm to network-based intrusion detection. So, what is a learning algorithm? A learning algorithm is an algorithm whose performances grow in time, during time. It can extract some information from past experience. I'm not an artificial intelligence type of guy. So when you hear me talking about learning, please think with me that we are talking about mathematical algorithms that choose the best parameters to fit some distribution of data. It's not that the machines are actually learning. They are simply tuning a function. So actually, the problem is, it's always the same, to choose the right function to describe this data and to choose a proper way to train this function. And there are two macro categories of algorithms and training functions: supervised and unsupervised algorithms. Basically, when you are training a supervised algorithm, you show it an example and say, this is a good packet. Then you show it another example and you say, this is a bad packet. And you go on this way. So you can think of your favorite Bayesian anti-spam filter if you need an example of supervised learning algorithm. So you are actually showing it both examples of good and bad things. The problem is, if you think again of the anti-spam algorithm, you need spam and ham to train it. You cannot simply tell him, this is spam, this is spam, this is spam, because it will flag as spam everything it catches. You need to train it to both sides, and you need an awful lot of training also. It's not easy to think to train an algorithm on network data if you need supervised training. Additionally, if you think about this, this is a form of generalized misuse detection. We are not training the algorithm just to understand what is normal, but we are training it about what is normal and what is abnormal. And basically, what we are realizing is a system which can extract the misuse detection rules without actually being taught about these rules. We are just showing it the bad things and letting it understand which are the rules to detect these bad things. If we want to create an anomaly-based, a real anomaly-based detection system, we absolutely need a system which can be trained on just one set of things, just on the good set of things. This can be done also with some supervised algorithm, with a very, very little subset of supervised algorithm. But it can be done very, very well with unsupervised algorithms. An unsupervised algorithm learns on unlabeled data. We present it with a choice of data, and it organizes the data according to some criteria into different groups, into different portions. There are unsupervised learning algorithms that are studied to learn the normal behavior of a system and detect variation. This should remember something. But how can we employ this type of algorithms of networks? This is the focus of my research. What they have been used for? They have been used for an awful lot of things. For example, a task unsupervised algorithm that very, very good at is to find groupings of X's, where X's have been human languages, types of stocks, gene sequences, animal species, whatever you want, you name it, they've got it, in order to discover some hidden underlying properties of these things. For example, in order to discover strange correlations between stocks on the market, or in order to discover strange correlations between human languages, which can help in reconstructing how the language is developed. Another task they are usually very good at is to summarize some data over time in a visually helpful manner. You are a scientist. You have obtained a lot of data, which has a lot of dimensions. You need to begin to understand how this data is organized, to begin to understand what you are really looking for. You can use one of these algorithms to present this data to you in the most visually helpful manner it can find. Another thing they are very good at is sequence extrapolations. So we are given the data for some past period, and we want to understand what will happen in the future. Which are the types of clustering of learning algorithms? There are clustering algorithms, which are the algorithms we create that grouping of data we have talked before. There are the so-called novelty detection algorithms, which are algorithms that hunt for outliers, for data that are totally different from what they have seen before. There are trend detection algorithms that actually are not really unsupervised learning algorithms. They are fitting algorithms that have been studied for decades. And then there are time series and association rule discovery algorithm. So what is clustering? Clustering means grouping some vectors of data into sets, maximizing the similarity of the things that are in a single set and minimizing the similarity of things that stay in different sets. It's exactly the task we can do very naturally. When presented with a set of objects, we can compare them and then put them together according to some criteria. So what is a pattern vector? It's what a database people would call a tuple, and it's a set of measurements related to something, which means that, for example, we are examining persons. We can examine a person's credit parameters and create groupings of persons based on that. If we are examining a TCP/IP network, for example, we could pick up the packet header fields of different packets and organize them based on that. The problem basically is to understand what similar means. Similar means close. Close brings the concept of distance. So if you have to understand how distant are two things, well, a basic distance is the Euclidean distance, what we usually do to calculate the distance of points on a plane, for example, or in a space. But it's not always the best type of distance. For example, if you have a genetic sequence and you have 3 letters of the genetic sequence, you could, for example, say that A means 1, T means 2, C means 3, and then calculate the distances. But this does not really make sense, because an A is not closer to a T than it's to a C. Okay? So in this case, for example, we are actually more interested in knowing the so-called matching percentage. We have 2 sequences of letters. We want to know how many letters are similar in the 2 sequences. There is the Manhattan distance, which is also called 1 norm. That means simply adding the distance on the various axes of your graph without raising them to square. And there's an awful lot of other distances. Basically, what happens is that based on the type of data you have to design a correct distance in order to create a correct clustering algorithm. As an example, I've prepared a couple of slides to show you how a clustering algorithm, a very basic clustering algorithm, which is called k-means, works. You have a set of points, in this case, bidimensional points, because it's easier to understand, which means that these points represent 2 different variables. For example, temperature and humidity in a given city in various periods of time. 2 variables for a single measurement. So what we want to do is to create groups, natural groups of points. And I excuse myself if I do not have a laser pointer, but if you look at the screen, you will see that there are 3 very natural groupings of points, because they are separated by a little distance, actually, but you can see that there is one in the lower corner of the axis, one straight above, and one to the right. In the case of k-means, we need to give it as a starting variable how many clusters, how many groups we do think there are in the data set. And so, in this case, just for the sake of an example, I have given it the right number, 3. Additionally, the algorithm selects 3 random points from the data set. I didn't select 3 random points. I choose 3 very good points, because in this way the algorithm converges in 3 slides. But in a standard real-world application, it could choose 3 points at will. Then what it does is that, based on the 3 starting points it has generated, it assigns points to the nearest cluster. And what you see on the graph is that the points have been assigned more or less to the correct cluster, because I chose the right points to begin with, except for one point, which is the lowest one, which has been assigned to yellow cluster and more naturally would fall into the blue cluster. In the next step of the algorithm, it picks up all the points in a single cluster, calculates the medium point of the cluster, which is called the centroid, and moves what at the beginning was initialized on the 3 random points to the centroid. So the 3 random points become a normal point, and we begin again with the new centroid, recalculating which points belong to which cluster, recalculating centroids, and going on this way until convergence. In this case, convergence is right here. This may seem a pretty useless algorithm, something which every human can do, tracing 3 bars on the graph, but teaching a computer to separate clusters of variables is not an easy thing to do. K-means is just one of the easiest algorithms. There are more refined ones. I chose it as an example because it was one of the easiest to grasp. But how do we choose the right algorithm for a task? Well, to begin with, we need to understand if we know in advance how many clusters are there in the data set. And this can be true in some cases. We have generated the data set before, and we knew that there were just 3 clusters. But if we are exploring an unknown data set, we do not know in advance how many clusters are there. K-means works only if we know very well K-means. Other algorithms, instead, can generate by themselves the correct number of clusters. In addition, we must understand if each point will end up belonging in a single cluster, or it can belong to multiple clusters, or maybe if clusters have a hard limit, either a point is in or it's out, or if they are simply expressed as a likelihood of belonging to a single cluster. Finally, there are very, very good algorithms that can do marvelous things, but simply do not handle very well scaling up with a 9 number of dimensions or a 9 number of data points, or they are simply slow. And this is important to us because if a data miner typically has got state-of-the-art hardware and a lot of time to conduct this research, we do have a network which is running, and we must try to keep up. We need the algorithms that are speeding, classifying things, but we can afford them to be lengthy in the training phase. Not very, very difficult to train, but they can employ some time. What's an outlier? An outlier is usually defined as an observation which is so different from the other observations that actually it makes you suspicious that it's been generated by something else, or it's an error in measurements. If we are observing packets, if our observation of packets, our hypothesis is that attacks are outliers with regard to the normal flow of packets. Why? Well, basically because if they are not, we can very well close my laptop and go home. But also because we have experiments that show that this is actually the case. There is a real number of algorithms for outlier detections. And as we will see in a couple of slides, attacks, some attacks, a lot of attacks, are outliers. There are algorithms that are capable of learning a multivariate time series, which is an awful mathematical word for a simple concept. A time series is a sequence of observation of a variable made over some time. Multivariate means that you have a lot of variables observed over some times. If a packet is a vector of variables, a packet flow is a multivariate time series. And what's an outlier in a time series? Well, the problem is that there are a lot of algorithms for detecting outliers, but not in time series. And there are a little number of algorithms that using something which you don't really want me to go into, which is called wavelet transforms, to detect outliers into multivariate time series. But we have seen that this type of algorithms are not adequate for our type of environment for 2 reasons. The first reason is that they are multivariate, but not so multivariate. They handle very well a little number of dimensions, but they do not scale. And additionally, in most of the times, they do catch just very, very huge outliers, something you would catch anyway. We are interested in more non-standard outliers, which are composed sometimes of a single packet. And wavelet transform do not really work well on that. Instead, what we do is to cluster a time series, which means that we pick up a time series, so you have the 5 packets on the left, each packet with its own variables, and we shift them into a rolling window. In this way, in this case, 2 packets, one after the other, the last 2 packets on the network, are picked up as a multivariate vector and are clustered exactly as if they were a single observation. Which means that, using this trick, we can use any of the clustering algorithms, which are an awful lot and which work very well and are also fast most of the times, to cluster time series, to detect variations in time series. There is also another set of algorithms which has been used for this type of things by us, which is association rules discovery, This is something you may have seen if you have taken classes in databases or data mining, because it's something they usually teach, which means that the objective in this case is to find rules that associate sets of events. So if we have variable x and variable y, we will also see variable z. They can be used in unsupervised and unsupervised manners, mostly in supervised manners, and they have been used in intrusion detection before. There is a system which is called ADAM, which is more of a log analysis thing, actually. But it's based on association rule discovery. And guess what? It's supervised. Another problem which grows up, and this applies also if you are not playing with clustering algorithms as I am playing, but if you are playing with other types of learning algorithms. If you present to an algorithm a really huge lot of dimension, a huge lot of variables, some of which are not really correlated with the event you are trying to describe. For example, you are trying to create a model which models the climate of a city, and you put into temperature, humidity, temperature of the sea, wind, number of people traveling through the area every year, number of cars propelled by GPL into the area, and so on. The variables which do not really mean anything tend to have two probable outcomes. Either you are very lucky and you discover a new relationship which makes you win the Nobel Prize, or you end up confusing the algorithm. You present to it a lot of variables which do not have really anything to do with the problem at hand, and what turns out is a function which does not really describe your model. In addition, in the particular case of unsupervised learning algorithms, if you add a lot of variables, usually training time to convergence grows exponentially. No one trains algorithms to convergence because that takes too much time. You usually end up selecting a stop criterion. At some point, you stop. But if the training time to convergence is very, very long, that means that if you stop too early, you will have a non-converged description of the model, which is not really useful to anyone. In addition, our experiments show that detection rate falls dramatically if we simply put every type of data we have into the same algorithm. The algorithm gets confused. It doesn't detect anything in a sensible way anymore. In addition, since already computational efficiency is a real problem for us, for keeping up to the speed of networks, actually the prototype we have is running very well on a 10 megabit per second network. It's handling a 100 megabit per second network with some faults, but it would never be able to handle a gigabit network. So if you add features, the performance of the algorithm invariably decreases. And if the algorithm is already to be optimized at its most to get up with the network speeds we need, then you end up with something which is very, very efficient, but useless, or something which is very, very good at detecting attacks, but useless all the same. So we have then an hard problem, a very hard problem, which is the reason why no one has experimented very well with training algorithms and unsupervised learning algorithms and network data before. That's because a network packet has an unstructured payload of data of varying dimension. It can contain basically anything. learning algorithms instead like data of fixed dimension and possibly small. Common approach to the problem by many of the other scientists in the field was we discard the packet content. We just look at the packet header. Now, I don't think I need to explain to any of you why that is bad. I had to explain, actually, that to a lot of other persons out there. It's unsatisfying, because most of the things we are really interested in are in the payloads, so we are throwing away what we really interest us. What we have found to be a solution is to use two algorithms, a clustering algorithm and another learning algorithm. What is the overall architecture then? We pick up the payload, which has an unstructured, too long, unmanageable length. We pass it through a clustering algorithm, which is capable of handling sequences of characters of different dimensions. In particular, we use a self-organizing map. And we obtain 1, 2, 3 results, 3 bytes of classification, which are a structured, fixed dimension, which can be added to the information extracted from the header and presenting to any of the learning algorithms that other people before us had experimented with, discarding the packet content. Why are we doing clustering? Is that really useful? Yes, it is. Here you have, on the left, the clustering of a window of 20,000 or so packets on 100 of classes. Which classes? I do not know. It's an unsupervised learning algorithm. God knows what made it cluster those packets in that form. But what is interesting is that you present to the algorithm just packets destined to port 21. You see that they fall in a very, very narrow range of classes. This happens with port 21. It happens with port 80. It happens with a lot of very, very structured protocols. So what this means to me is that packets into the FTP command sessions, but into a lot of other protocols, FTP is just the best case to show because it's very graphically impressive, contain a structure which an unsupervised learning algorithm is very good at detecting. Cool. Now, what happens if I inject instead some attacks against FTP servers on that channel? I have reported about a couple of interesting attacks. The first is the format string vulnerability. I'd like to stress again that we did not give to the system any description of this vulnerability. So, for the system, it's a zero-day attack. We do not have zero-day attacks to use to test our system. But if we do not give a priori knowledge of the attack to the system, clearly it's a zero-day attack for it. The payload of that attack was classified in class 69, which on this type of screens is really unreadable, but I can assure you that is not one of those classes over there. So we have a packet belonging to an FTP session which falls totally outside the normal characterization of FTP packets. That's an anomaly. Also interesting is the globbing attack, which is an attack which is very, very polymorph. Basically, you can build your own string for exploiting this attack. You put together a lot of backslashes, wildcards, dot, wildcards, and so on. As long as you construct a path with a lot of wildcards, which has some meaning for a Unix system, it will try to expand it, and it will crash. But you can build a string to exploit this attack, which is always different. If you want to write a signature for snort for this attack, the only reasonable way you have to match it is to match \wildcard, which is not very, very used into the normal FTP transactions, but could theoretically be part of a legitimate command. And so this is an example of an attack which either you disable the signature for snort, or you get prepared for a flood of false positives. The SOM classifies all the variants we tried of these attacks. We didn't try all the variants, because this would be rather lengthy, since they are infinite. But it classified all the variants in the same class, class 97, which, guess, it's not a normal class for port 21. It's an outlier, again. And we tried this with some other attacks. Many of them fall outside the normal classification. A lot fall inside the normal classification. I'm not pretending that a system of this type, especially alone, can detect a high rate of attacks. However, it can detect a number of attacks, very different, without a priori knowledge. And this is a prototype, a very, very awful prototype. Most of the things I have shown here, nowadays we have a small prototype written in C++. Most of these things were elaborated using MATLAB. So this is really research which is being done in this very moment. But we have had a lot of good and interesting results from it. What we are doing right now? Well, first of all, we are still experimenting with good candidate algorithms for second tier. As I said before, any of the algorithms which has already been used for the simple header of the packet can be complemented with our algorithm and used again. And we have had some interesting results. On the same data set, we have had 75% increase in detection rate. Also an increase in false positive rate of about 20%. On the false positive, of the previous false positive rate, not a false positive rate of 20%, which would be rather alarming. But what happens is that we have showed that adding this additional stage basically improves the detection rate of the other algorithms. So it's just a matter of choosing the best fit algorithm. One of the problems here is that we noticed that most of the other people who have worked on this type of things, and most of the papers we have based our own research on, do not really care about runtime of the trained algorithms, which is a real problem for us because we are trying to build a real intrusion detection system and not something which runs just on paper. So what are the conclusions and what is our work? We have concluded that based on the observation that I've shown you before, if we need IDS, we need them as a complementary paradigm. If we need them as a complementary paradigm, we need them to detect unknown attacks, or polymorph attacks, or attacks that are creatively exploited in a new way. If we need that, we need an anomaly detection system. We can use unsupervised learning algorithms for anomaly detection systems. There are a lot of problems to deal with. We have dealt with at least one of these problems, which was to reduce the TCP payloads or the IP payloads to something meaningful. And we have obtained the improvement on the detection rate for earlier systems. What we are going to do now is to try to find a good candidate for the second stage, which also really works sometimes. we are studying the signal-to-noise ratio to understand which variables can be tuned in order to reduce false positives. We are also integrating our system as a Snort plugin because basically it was the easiest thing to do. We do not want to rebuild another intrusion detection system. It's good as a component of Snort. What we are finding, I wouldn't say problem, I'd say challenges in, is to write these algorithms in a way which is truly compatible with the task of managing a high-speed network, because they are not studied for that very purpose. So we are also improving some of these algorithms and optimizing them. And we have integrated it into the architecture of STAT. I do not know if it's a known system. It's an academic project going at the University of California, Santa Barbara, which is another misuse detection system. Basically, we complemented it with some anomaly detection features using this type of algorithms. This is basically all I had to say. I hope I didn't tire you too much. I hope you enjoyed the talk. Thank you very much for your attention. And again, I would greatly appreciate your feedback. Constructive feedback is more appreciated, but if you feel like flaming me, please do so. My address is on the slides, and if you are interested in reading some other papers and knowing about some other research areas of the Politecnico di Milano Performance Evaluation Lab, that's my web address. It's awful, I know. It won't be working this weekend because they are going to shut down the electric power in the whole university for 2 days. Don't ask you. Pray don't ask. And nothing. Thank you very much.